Welcome back. In this chapter, we're going to be introducing the idea of sequences and series. A sequence simply is a list of numbers. It's an ordered list. There's a first number, a second number, a third number, and a fourth number, and so on. And what we're going to be doing in this section is introducing ways to formally talk about these sequences. So one way you could think about a sequence is as being a function where the domain is positive integers, 1, 2, 3, 4, 5, and so on, and the output, that would be the numbers that are on our list. So for example, if you're thinking about this sequence that we have that has the numbers 2, 4, 6, 8, 10, and so on, if I wanted to formally talk about that as being a function, I could think of 2 as being the first number in the sequence. It's the number that 1 will map to. 4 is the second number in the sequence. It's what 2 maps to. 6 is the third number in the sequence. That's what 3 maps to, and so on. So one way that we can talk about it is by describing it as a function. I can say f of n is 2 times n, where n is a positive integer. So for example, when n is 5, f of n would be 2 times 5, which is 10. So we would have our fifth number in the sequence being 10, and we can see that there. Now, when we're looking at sequences, there are both infinite sequences and also finite sequences. So the list that I've got there, 2, 4, 6, 8, 10, with dots, showing that that list goes on forever, that would be an infinite sequence. But a sequence can also just be a finite sequence. We might only have a finite number of things in that list. Now, there's a couple of other styles for notation that we can have for a sequence. So this style that we're using here, this function notation style, that's maybe not the best choice for us, because if people are looking at that, they might think that n might be able to be other things other than positive integers. So it's kind of nice to have a notation style that's just for sequences. And that's what we're going to introduce here. This idea of using a name for our sequence. Just like how we had for a function, I could name a function f. We can name a sequence with a single letter as well, and use subscripts to talk about what position on the sequence we're talking about. So for that same sequence of numbers, 2, 4, 6, 8, 10, and so on, one way I could define it is in terms of that function notation, saying that f of n is 2n, or instead I could say a1 is 2, a2 is 4, a3 is 6, and so on. I can describe the terms in my sequence. a1, that's the first term in my sequence, happens to be 2. a2, that's the second term in the sequence, which is 4. a3, the third term in the sequence, which is 6, and so on. So something like that number 10, I could say that that is a5. a5 is the fifth number in my sequence, and that happens to be the value 10. So the other notation that we can use for a sequence would be this notation, where I say that the set of all things in that sequence an, that's, notice I've got curly brackets there, so it's the same set notation that we've used before. So the set of all numbers that are in my sequence an are the set of numbers that have the form 2 times n. That's what that notation is telling me. So when I say an is equal to 2n, really what I'm doing is I'm giving a formula, again, for the terms of my sequence. I could also use, without the set notation, I could just say here's the formula that gives you the nth term in the sequence, so that an is just 2 times n. Okay, so if we have a formula given for us, then it's not too hard to find the first however many terms we'd like in the sequence. So for example, with the first one, an being 1 over n squared, a1 should be 1 over 1 squared, which is 1. a2 should be 1 over 2 squared, which is a quarter. a3 should be 1 over 3 squared, which is 1/9. a4 should be 1 over 4 squared, which is 1/16. a5 should be 1 over 5 squared, which is 1/25. And a6 should be 1 over 6 squared, which is 1 over 36. So once we have a formula, it's easy enough for us to come up with the values on our sequence for each of the terms that we're looking for. Next one up, if we're looking at bn, so that's 2n minus 1 over 2n. So b1, that would be 2 times 1 minus 1 over 2 times 1, which is, if I simplify that, that's 1/2. b2, that would be 2 times 2 minus 1 over 2 times 2. That would be 3/4. One of the nice things about sequences is that we might start to notice a pattern, and so after we've done a couple of these, we might be able to see what the pattern is so that I don't have to keep doing all of these calculations. So once I've gotten to b3 and I find that b3 is 5/6, I might notice that for the numbers in my sequence, I've got 1/2, 3/4, 5/6. I notice that the denominator is going up by 2 each time, and the numerator is also going up by 2 each time. So without having to do extra work, I can now say, well, b4 should be 7 over 8. b5 should be 9 over 10. And b6 should be 11 over 12. And of course, I can confirm that just by using the formula that I have for bn. Now we've got one last one to do here. That's cn. That's negative 1 to the n times 1 over n. So c1, that's negative 1 to the 1 times 1 over 1. That's just negative 1 over 1, or negative 1. c2, that's negative 1 squared times 1/2. Negative 1 squared is positive 1, so we'll get positive 1/2. c3, negative 1 cubed times 1/3. Negative 1 to odd powers stays negative, so we'd have negative 1/3. At this point, you might notice, as I'm writing here, that things are alternating, that we're alternating between positives and negatives, that all of the odd terms of the sequence, the first term, the third, the fifth, and so on, those are all going to be negative, and that the second and the fourth and the sixth and all of those terms, they're all going to be positive. And that's exactly what we see here. So if we're putting together a sequence that's alternating, like this one is, then the formula for an alternating sequence, one that goes between positive and negative back and forth, that's going to involve a minus 1 to a power, and that's what gives us the alternating part of our sequence. So just finishing things off here, we've got C6 is 1/6 positive. So there we go, we've got ourselves a nice alternating sequence. So now, of course, you want to be able to do the reverse, which is if you have a sequence, to come up with a formula for the nth term. So this takes a little bit of work because instead of having a formula and just putting numbers in, we have to figure out what the formula should be. And that takes a little bit of looking at the numbers themselves. So if you're looking at the formulas the terms of the sequence that we have for A1, A2, A3, and A4, one thing you might notice is that all of these denominators, these all happen to be powers of 3. That's 3 to the 1 in the denominator, that's 3 squared, that's 3 cubed, that's 3 to the 4. And the other part that we might notice is that in the numerator, the numerators are also powers, this time powers of 2. You've got the numerators 2, 4, 8, and 16. Those are 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. So I'm looking at this, that A1 is 2 to the 1 over 3 to the 1. A2 is 2 to the 2 over 3 to the 2. A3 is 2 cubed over 3 cubed. A4 is 2 to the 4 over 3 to the 4. So I can see my pattern right now. I can see that whatever term I'm looking at, term n will have 2 to the power of n over 3 to the power of n. Once I've come up with my formula, or once I've come up with what I think is my formula, I can confirm my answer because, of course, I know what A1, A2, A3, and A4 are. So if I want to confirm, am I correct or not correct, all I have to do is ask myself, if I put in 4 for n, do I get 16/18ths? If I put in 3 for n, do I get 8/27ths? The answer is yes, and so for that, I can feel fairly happy and fairly confident that I've got the right formula. So we're going to do the same sort of a thing for the next one. We're going to come up with a formula for this alternating sequence. And so one thing I notice again is that here I've got 2, 4, 6, 8, 10, 12. So that's 2 times 1, that's 2 times 2, that's 2 times 3, that's 2 times 4, and so on. So the first term has a 2 times 1 in it, the second term has a 2 times 2 in it, the third term has a 2 times 3 in it. I can start making a prediction that term n is going to have a 2 times n in it. So at the bare minimum, I can see that for my sequence Bn, there is going to be a 2 times n. There's also the alternating part that we haven't talked about, that some of these terms happen to be negative. B2 is negative, so is B4, so is B6, and so on. We know that if we've got a sequence that's alternating, there's going to be a negative 1 to a power involved in it. If I had that power being n, then what that would do would be whenever n is an odd number, 1, 3, or 5, or so on, negative 1 to an odd power would stay negative. So if I had negative 1 to the power of n, that would make my first term negative, which unfortunately it is not. So that means I'm not quite right with my formula. I know that it's not the first term that needs to be negative, but the next term, the second term, that's the one that needs to be negative. So instead of having negative 1 to the power of n, I'll have negative 1 to the power of n plus 1. And so now I can just double check that when B1, when I'm looking at that term, that would be negative 1 to the 1 plus 1 times 2 times 1, and that indeed is equal to positive 2. So I feel like I've got the right formula. Double checking, does it give me the right number for B2? That would be negative 1 to the 2 plus 1, which is 3, times 2 times 2. That should give me negative 4, and that, yes, that is my second term. Okay, I now feel confident that I've come up with the right formula. Again, the nice part about a lot of this is, since you have the numbers in the sequence already, you know the first, second, third, fourth, fifth, and sixth term. Once you've come up with a hypothetical formula for Bn, you can actually confirm to see, is your formula correct? All right, last one here, I've got C, and that's this sequence. The first term is a half, then we've got 2/3, then 3/4, then 4/5, then 5/6, and so on. So one thing I'm noticing here is the top is always 1 less than the bottom. So 2 and 3, 3 and 4, 4 and 5, 5 and 6. So I do have one little relationship that's already kind of obvious there. Numerator is always 1 less than the denominator. The other thing that I notice is that for the first term, the numerator is 1. For the second term, the numerator is 2. For the third term, the numerator is 3. The fourth term, the numerator is 4. So that's making me think that for term n, the numerator should be n. And the next part I know is that the denominator should be 1 more than the numerator. So if the numerator is n, then the denominator should be n plus 1. And so I've got my, what I think is my formula, and I can just double check to see, does it generate the terms in the sequence that I've been given? When n is 1, do I get 1/2? Yes, I do. When n is 2, do I get 2/3? Yes, I do. So I can feel confident in what I've got. I can say, yes, it looks like my formula is generating the terms in my sequence. And so I can say that, yes, there we go. We've got a nice formula here for Cn. Another way that we can define sequences is recursively. So instead of giving a formula that says, here is an in terms of n, so that's what we had here. We had formulas for an that were given in terms of n, so you just had to put in values of n and you can generate the terms of the sequence. For a recursive definition, this is defining one term of the sequence in terms of previous terms of the sequence. So when we're looking at something that's a recursive definition, there's two parts to it. In a recursive definition, we give something that tells us how does the sequence begin, the initial term. So that's what we have here in part A. We know that the first number in our sequence is 3. And we're also given a relationship. This relationship tells me that if you want to know the number of term n, then you need to know term n minus 1, and whatever that term is, you're going to multiply it by 2. So in other words, this is a little recipe of how to make the next term in the sequence using the one that you currently have. If you want the next term in the sequence, take the last term in the sequence and multiply it by 2. So a2 should be 2 times a1, which is 2 times 3, which is 6. a3 should be 2 times a2, which is 2 times 6, or 12. a4 should be 2 times 3, which is 2 times 12, or 24. a5, that's 2 times a4, which is 2 times... There we go. 2 times a4, which is 2 times 24, or 48. And last one, a6. a6 is 2 times a5, which is 2 times 48, or 96. Now you can also have a recursive definition that's not just in terms of the previous term, but maybe the previous two terms. That's what we've got going on here with this recursive definition. It says that if you want term n, then you need to take terms n minus 1 and terms n minus 2 and multiply them together. So in other words, if you want a current term, you need the two previous terms and you need to multiply them together. And so that means that you need at least two terms to start this off. That's why we have two initial terms given to us, the first term and the second term. And once we know the first term and the second term, we can use them to generate the third term. b3 should be b2 times b1, which is 2 times 3, or 6. b4 should be the two previous terms multiplied together, b3 times b2, which is 6 times 3, which is 18. b5 is the two previous terms multiplied together, b4 times b3, that's 18 times 6, and that turns out to be 108. And lastly, b6, the sixth term in the sequence, we have the previous two terms multiplied together, b5 and b4, so that's 108 times 18, which is 1,944. All right, one last one. So the previous one, we had a sequence made from the previous two terms multiplied together. For this one, term n is made by taking the previous two terms and adding them together. So if we're looking at finding term 3, a3, we'll need to take a1 and a2 and add them together. And we already have a1 and a2 given. a3 is a2 plus a1, which is 2. a4, that's the two previous terms added together. a3 plus a2, that's 2 plus 1, which is 3. a5, that's the two previous terms, a4 and a3 added together. That's 3 plus 2, which is 5. And last one, a6, which is the previous two terms added together, a5 and a4, which adds up to 8. This sequence, 1, 1, 2, 3, 5, 8, and if you kept on going, 13, 21, 34, 55, and so on. This is the sequence called the Fibonacci sequence, named after an Italian mathematician from the 1200s. One thing that's kind of a nice fact is that the numbers in the Fibonacci sequence show up in a lot of things in nature. It's kind of a fun little crossover between math and everyday life. And one other thing as well is that this sequence has a nice little property that if you were to take the ratio of consecutive numbers in the sequence, like 3 divided by 2, or 5 divided by 3, or 8 divided by 5, when you take these consecutive terms in the sequence and take the ratio of them, as it turns out, the ratio that you have gets closer and closer to this constant, 1 plus root 5 over 2. And it's a ratio called the golden ratio. It's been used in art and in architecture. So anyhow, that's just a little aside, not a major important feature, but just a nice thing to notice as some famous sequences out there. One last thing that I want to introduce here in this section is an idea called the factorial. A factorial is a special function, and you could describe a factorial recursively in the same way that we described our sequences in the past. So when we're defining a factorial, we define the first two things. We say what 0 factorial is. We've defined that to be equal to 1. And what 1 factorial is, we define that to also be equal to 1. So for this function, the factorial function, it's a special product of consecutive positive integers all the way down to 1. So when I say n factorial, this is all the positive integers from 1 up to n all multiplied together. Now, you can say you can define things recursively here because you might say, well, you might notice that the numbers from 1 up to n minus 1 all multiplied together, that's really the same thing as n minus 1 factorial. So you could say that n factorial, instead of being 1 up to n multiplied together, that it's really n times n minus 1 factorial, and that's a nice little recursive definition that you can give to it. So something like 0 factorial and 1 factorial, we know what those are because by definition, we've said that 0 factorial is 1 and that 1 factorial is 1. But for something like 2 factorial, well, that would be 2 times 1 factorial, which is 2 times 1, or 2. 3 factorial, that's 3 times 2 factorial, which is 3 times 2, or 6. 4 factorial, that's 4 times 3 factorial, 4 times 6, which is 24. Also notice that that's the same thing as 1 times 2 times 3 times 4. So whether you're using the non-recursive definition or the recursive definition, you get the same values either way. A5, sorry, not A5, 5 factorial rather. 5 factorial should be 5 times 4 factorial, which is 120. And 6 factorial, that's 6 times 5 factorial, that is 720. Just as an aside, you do have a factorial function on your calculator. If you're looking at your calculator, you'll see right above the number 4, you'll see a little n factorial symbol. So if you wanted to use your calculator to find, for example, 6 factorial, you could enter 6 second function 4, and then in your little display window you'll actually see a 6 with an exclamation mark show up when you touch the second function in 4 to bring that factorial function up. And then when you hit equals, it will give you the 120. Factorials are kind of important. They show up in a lot of places in mathematics, and there's a couple of really important places where they show up. Namely, if we're thinking about something like counting problems, so if you have taken a math class where you are talking about probability or counting, You do use factorials in counting problems where you're looking at arranging objects. So another way that you can describe what a factorial does, instead of just saying, oh, it's a bunch of numbers multiplied together, concretely what it actually is the number of ways that you can arrange n distinct objects. So the example that I have here, if you have 12 students and I want to line the 12 students up for a photograph, and I want to know how many different arrangements I have of those 12 people, then since I'm arranging 12 distinct objects, that can be done in 12 factorial ways, which is 479,001,600. There's lots of different arrangements. It also shows up in a bunch of other places too that don't necessarily have obvious connections to counting. If you're remembering our original definition of how we gave the number e, that mathematical constant, we defined it in terms of 1 plus 1 over n to the power of n, what happens when n becomes very large. Another way that you can define E is in terms of this infinite series. We're going to talk about this a little bit later on in chapter 13.4. When you have a sum of terms of a sequence, we call that a series, and this is an infinite series. So if you were to take all the reciprocals of all the factorials and add them all together, as it turns out, that gets closer and closer to e to the power of 1 as your number of terms goes and gets infinitely large.